This is essentially a continuation of my previous lecture, and I have derived expressions for these integrals, the integral here and the integral there, and I have removed everything that I do not need from the previous lecture, and I am left with this expression for the numerator in here and that expression for the denominator. So, therefore, if you substituted these expressions, you are going to get C A square H A A plus C B square H B B plus divided by C A square plus C B square plus 2 C A C B into S. But what is S? I would like to remind you what S is. S is defined to be integral d2 1sa 1sb, product of 1sa and 1sb, and often there is this question, why is it that this integral is not 0? Because you normally learn that if you multiplied any two atomic orbitals and integrated them over the entire space, the answer is actually 0. Now, if the orbitals belong to the same atom, that means if I had taken, let us say, 1sa and multiplied it by 2sa, where 2sa is an atomic orbital on the same atom, and integrated over the entire space, the answer will be equal to 0. But 1sa and 1sb are not on the same atom, they are on different atoms. And further, what is the shape of 1sa? 1sa is having this kind of shape, and how is 1sb? Well, this is 1sb, right. So, therefore, in this integral what you are actually doing is, maybe I will use different colors. This is 1sa and that is 1sb. And remember, everywhere both the functions are positive, this is positive, 1sa is positive, 1sb also is positive. So, therefore, you are actually multiplying two functions which are positive, and therefore, what will happen? The product will actually be positive, and you integrate. Integration is just a process of summation. So, you sum over all points in space, what is the result? The result can only be positive, it cannot be 0. Okay. And further, when you multiply the two functions, where is it that the product has the largest value? Well, if you are thinking of a point somewhere here, see there the distance from nucleus A is not large, and therefore, 1sa will have a fairly appreciable value, but the distance from the other nucleus is large, and therefore, 1sb will have a small value, and therefore, what will happen? The product will have a very small value at this point or at that point, because you see the distance from nucleus B is large. Similarly, if you think of a point here, there again the product will have a very small value, because the distance from nucleus A is large. But if you are thinking of this region which is in between, there the values of 1sa and 1sb are appreciable, because the distance from nucleus A and nucleus B, both of them are not large, and therefore, when you think of the product will have a large value in the internuclear region, that is the region where the two orbitals we say overlap, the region where the two orbitals overlap. So, essentially this integral is a measure of how strong the overlap between the two atomic orbitals is, and because of that this integral capital S is referred to as the overlap integral. And it gives you an idea of how strong the interaction between the two orbitals is basically. So, now what we will do is, having defined this overlap integral, let us proceed. We have our expression for script E, and what should I do now? I have to find out, or I have to think of CA and CB, right. I have to think of script E as functions of, as a function of CA and CB, and then find the maxima or minima of this function. In fact, I should find the minimum of this function. How will I do that? The answer is that I will have to put dou E by dou CA equal to 0. I think it is already written here. I will have to put that equal to 0. I shall also have to put dou E by dou CB equal to 0, right. These are the two conditions to have a minimum. Now, this means that I have to take this expression, right. This expression I will have to take and differentiate that with respect to CA, put the derivative equal to 0, and then differentiate that again with, once more with respect to CB and put that derivative equal to 0. Okay. Now, this looks like a tedious thing, because you have to differentiate a ratio, but what we will do is a simplifying trick. My script E is given by this expression. So, instead of differentiating that expression, what I will do is little bit different. I will first multiply this function, I will multiply this equation throughout by this factor. So, if you did that multiplication, what is the equation that you are going to get? You will get script E into CA square plus CB square plus 2 CA CB into S is equal to CA square H AA plus CB square H BB plus 2 CA CB H AB. This is what you will get, right. Now, having got this equation, what I will do is I will just go ahead and differentiate, because after all I just want to find the derivative of script E. So, now with this equation, suppose I differentiated this equation with respect to CA partially, then what is the result that I am going to get? Well, from the left hand side you are going to get dou E by dou CA into CA square plus CB square plus, oh, yeah, this is correct. I thought I had made a mistake, right. If you differentiated the left hand side, you will get derivative of script E with respect to CA plus script E into the derivative of this term with respect to CA. Remember, I am differentiating partially with respect to CA. So, the derivative of this term will be 2 times CA. And remember, you are differentiating partially with respect to CA, that means the derivative of this term will be equal to 0. And what will be the derivative of this term? It will be 2 times CB into S. So, that is the derivative of the left hand side. What will be the derivative of the right hand side? It is going to be 2 CA H AA, because I am differentiating this term. If you differentiated this term, you will get the answer to be 0, because that term does not depend upon CA, and the last term will give me 2 CB H BB. Fine. Now, if I want, I can rearrange this expression. I can take this to the right hand side and then divide throughout by that term and get an expression for dou E by dou CA if I want. But that is unnecessary, because after all I am going to put this equal to 0. So, straight away in this equation I can put this equal to 0. And so, I get one equation. What is that equation? I put this equal to 0 and I get that this must be obeyed. Okay. And in that equation I can make simplifications, because 2 is common. So, remove that 2. And further you take the terms on the left hand side to the right hand side. So, what will happen if you did that? Take these terms to the other side. then you are going to get HAA, there is this term HAA into CA, but one more term will come because you have script E into CA, that I am taking to the other side. So, therefore, this minus script E will be the first term. And then there are two terms actually which involve CB. What will they be? The term which is already there. Okay, there is my mistake. This is actually, you are differentiating this with respect to CA, and the answer should have been CBHAB, not HBB. Here, right, this term gave you the answer 0, while if you had this term, if you differentiated that, you will get CB times HAB. So, therefore, what will happen is that you will have HAB minus script E into S as the other term, right, and these two things added together must give you the answer 0. So, how did I obtain this equation? I obtained this by putting dou E by dou CA equal to 0. This implied that I have such an equation. In a similar fashion, if you took the derivative of script E with respect to CB and put it equal to 0, what is the answer that you are going to get? It is fairly easy to write it down. You do not have to actually work it out, you can write by analogy, and the answer is going to be HAB minus script E into S into CA plus HBB minus script E into CB is equal to 0, correct. If you did exactly the same procedure, you are going to get this equation. And what should I do? I have to solve these two equations, and if I solved these equations, what is the good thing? The good thing is that I shall get the best possible values of CA and CB. Now, instead of directly solving it, I am going to write it in a fancy form. Okay. What I will do is, I will write this as a matrix equation. You will realize when I write this, I mean after I have written this, that this is nice. I am writing a matrix which is a 2 by 2 matrix. Well, strictly speaking, I should put a column matrix on the right side, saying that there is a 0 here and there is a 0 there, because if you look at this, you will realize that when you multiply this with that and put it equal to 0, you will get the first equation, and if you multiply this with that and put it equal to 0, you will get the second equation. Okay. Now, many a times people do not usually write 0 0 here, but instead they just write a 0, which actually means that you have a column matrix there. Now, this is what is done in the slide also. This can be written, these two equations can be written in a matrix form, and that is nice. The matrix form is shown here, but why do I say that it is nice? Well, this matrix equation is actually of the following form. See, you have a square matrix here and this is a column matrix. So, I can write it in this following form. I have a square matrix I shall indicate with a double underlining, and this is a column matrix. This A stands for this whole matrix, and the other matrix which I shall denote by the symbol C with one underline indicating that this is a column matrix. And A, so therefore, this is the form of this equation, A into C is actually equal to 0, strictly speaking I should put an underline there to indicate that it is a column, correct. It is a column of 0 and 0. So, you have a square matrix multiplying a column matrix equal to 0, that is the form of this equation. So, then what will happen is that I can say, okay, imagine I multiply from the left hand side with the inverse of A, right. So, I would have A inverse, and on the right hand side you would have A inverse multiplying 0, which after all you see if you multiply anything by 0 you are going to get 0. So, you are going to get 0 still. But what has happened to the left hand side? You have A inverse A inverse A is identity, and therefore, what is the result that you get? You will get this, the result that C is equal to 0, correct. Now, if C is equal to 0, what is C? C is actually this object, C is this column matrix. If you say that that is equal to 0, that implies C A is equal to 0 and C B also is equal to 0, right. And therefore, what happens to your trial function? C A is equal to 0, C B is equal to 0. So, you have trial function identically equal to 0. Is that acceptable? This definitely is not acceptable, because this means that your wave function for your electron is 0 everywhere, and therefore, the electron is not anywhere, right. So, I mean this is the kind of comment that one can make. If phi is equal to 0, your electron is not anywhere, and therefore, definitely that is not acceptable. So, what is wrong with this analysis? See, I have assumed that A has an inverse. Now, if A has an inverse, then definitely C must be equal to 0 by this argument. So, therefore, what is the conclusion? The matrix A must be such that it does not have an inverse. So, when is it that a matrix does not have an inverse? The answer is very simple. If the determinant of the matrix is equal to 0, then it does not have an inverse. If the determinant is non-zero, then you can always find an inverse. So, the conclusion is that if this equation is to give you sensible answers for C A and C B, then the determinant of this matrix must be equal to 0. So, let us take this determinant and put it equal to 0. So, what is the determinant? The determinant actually is magnitude of determinant of H A A minus E H A B minus script T into S, H A B minus script T into S, H B B minus script T. This determinant must be equal to 0, right. Now, this is very nice. Why is it very nice? Because originally I had two equations, C A and C B. I had two equations, one for C A and the other for C B, and the problem was to solve for C A and C B, and once I had obtained those best values of C A and C B, I would have to put them in here and find the value of script T. But now look at this, I have obtained an equation for script T directly. I have actually eliminated C and C B from the problem. I have just an equation for script T. So, if I solve this, I will get the best possible value of script T, right. So, I do not have to actually solve for C A and C B, that is why this matrix analysis is nice. And so, all that I need to do now is just solve this equation, right. Now, if you expanded this, if you expanded the determinant, what will you find? You will find that you have a quadratic expression in script T, and you are saying that a quadratic expression in script T is actually equal to 0. If you solve that, you are going to get two different values of script T, right. And then you have the problem, what will you do with these two values? Well, the answer is that you will look for the one that is lower, because that will be the best approximation for the ground state of the system. So, let us expand this determinant and see what happens. So, this determinant I can expand. What I will get is HAA minus script E into HBB minus script E minus HAB minus script E into S, right. You multiply these two, and from the product you subtract the product of these two, and this and that are identical. So, you will get HAB minus script T into S the whole square is equal to 0, and this is a quadratic equation. If I solve the quadratic equation, I am going to get two answers. Now, the analysis that I have carried out is fairly general. Even if I did not have a 1s b atomic orbital here, you see here I have assumed that this is 1s a and that is 1s b, and I have assumed that the two nuclei are identical. But imagine I have a situation where I have maybe one nucleus is a helium nucleus and the other nucleus, okay, one nucleus is a helium nucleus and the other is a proton. Even for that, if I assumed that I may take a linear combination like this, all the analysis that I have carried out can be pushed through without any difficulty. You will get this as the answer even for a more complex system, which has only two atomic orbitals. Okay. But now I am going to make use of the fact that the two nuclei are identical, right. I know that the two nuclei in this case, in the case of H2 plus, they are identical, and therefore, it is possible for me to use that fact and make some simplifications. So, you think of HAA and you think of HBB. What is HAA? Well, HAA is actually integral d2 1sa H 1sa. And HBB is actually integral d2 1sb H 1sb, right. Now, suppose I say that I am going to try the function 1sa as a trial function. Suppose I am going to say I am not going to take this linear combination Ca 1sa plus Cb 1sb, but instead I just want to use the atomic orbital as my trial function. That means, I am going to try phi to be equal to 1sa. That what will be the value of energy that I will get? The energy that I will get is integral phi star h phi d2 divided by integral phi star phi d2. This is the expression for energy that I will get. But now I am going to say no, my trial function is not such a combination, but it is just 1sa, and what will happen? I will get d2 1sa H 1sa divided by integral d2 1sa square d2, right. if for a moment you are going to say that the wave function for the electron is just 1 as a, it is not a linear combination, but it is just 1 as a, then the expression for energy that you will get is actually d tau 1 as a h 1 as a divided by integral d tau 1 as a square d tau, but this integral is unity and therefore, this is nothing but equal to h a. Now, this gives me a simple physical interpretation for this integral. Imagine that I have this H2 plus molecule and imagine that one electron is forced to sit in the atomic orbital 1 as a. Then its energy would have been this integral, and therefore, I can say that H A A is the energy of an atomic orbital, right, which is in a molecule. So, it is the energy of an electron in the molecule, but forced to sit in the atomic orbital 1 as a. And if I extended the same argument, H B B would be the energy of an electron which is forced to sit in 1 s B, but I know that 1 s A and 1 s B are identical, because the two nuclei are equivalent, the orbitals are equivalent. Therefore, whether I put the electron in 1 s A or 1 s B, the system should have the same energy, and this simple argument convinces me that H A A and H B B must be the same. You can actually evaluate it by actual integration, you will find that they are equal. But this physical argument tells me that H A A and H B B must be the same, and therefore, what should I do? I can put that here, H B B must be equal to H A A, and hence this equation becomes even simpler. The left hand side becomes H A A minus script E the whole square, because this and that are identical, minus H A B minus script E into S the whole square is equal to 0. Correct? Now, this is a quadratic equation, but this is a particularly simple quadratic equation, because what I can do is I can take this term to the other side and write this equation as H A A minus script E the whole square is equal to H A B minus script E into S the whole square. And if I wanted to find the value of script E, all that I need to do is I take the square root of both the sides. So, when I take the square root, I shall get H A A minus script E is equal to H A B minus script E into S. That is only one possible square root, one possible solution, right. But you have another solution where you will say that H A A minus script E may be the negative of the other term. That means, you would have minus of H A B minus script E into S. So, this single equation is equivalent to one of these two equations, right. Either this or that has to be obeyed. And if you took the first equation, you will get one of the possible solutions, while if you took the other sign, you will get the other solution. So, we will look at the negative sign first. So, what does that give me? It gives me H A A minus script E is equal to minus of H A B minus script E into S, right. If I took the negative sign, this is the answer that I will get. So, I can rearrange and get an expression for script E. What is the expression? H A A plus H A B divided by 1 plus S is the answer that you will get, okay, and for reasons which I will explain later. See, I am going to get one more solution for script T. So, I will like to distinguish between this solution and the other solution, and this solution I will put a subscript G, reason will become clear later. Okay. And if you took the other one, the other solution, this one, and solve for script T, you will get a different answer. Let me write that answer. I will put a subscript U for that, and if you did the rearrangement and solving, you will find that it is given by HAA minus HAB divided by 1 minus S. Fine. So, these are the two possible answers for script T. One I have denoted as EG and the other one I have called EU. And out of these two, which one would you expect is the best approximation for the ground state? Well, the way it is written, it would appear as if this is lower than that, because you see there is a negative sign here and you would expect that this is lower, but in actuality what happens is that all these quantities HAA, HAB, they are all negative, which is not surprising, because if you think of the energy of the hydrogen atom, it is actually minus 13.6. So, therefore, all these integrals HAA, HAB, they are all negative, and therefore, what happens is that this is the one that is actually lower, okay, and this is higher. Okay, now the next thing that I would like to do is, I would like to find the corresponding wave function. You see, it is not enough to say that this is the best energy, I should also know why this is the best energy, correct, that I should know. So, therefore, I want to find the wave function, I want to look at the wave function, and how will I do that? Well, I know that CA and CB actually satisfy this matrix equation, right? It satisfies this matrix equation, that was our starting point. So, in that matrix equation, I will imagine that this equation is obeyed, because that is my solution that is of interest, this equation is obeyed, correct, and that will actually give me the value of Eg. So, therefore, if I want to find out the trial function corresponding to this energy, this script E, I should take this equation and use it in my matrix equation. So, if I used that, what is the answer that I am going to get? HAA minus script E into S right. This equation tells me that this object multiplied by minus 1 is actually equal to HAA minus script E. So, therefore, the quantity that is occurring, there is no S here, HAA minus script E, then this one is actually the negative of the same object, correct. This is just the negative of this, that is what that equation says. And if we looked at the second thing, this part HBB is actually equal to HAA. So, this may be written as HAA minus script E, and this object is just the negative of that. So, therefore, this one will become minus HAA minus script E, correct. So, you realize that these elements are all simple, and this multiplying CA CB is actually equal to 1, correct. Oh, thank you, this is equal to 0. So, let us multiply things out and see what happens. So, if you multiply this, you are going to find HAA minus script E into CA minus HAA minus script E into CB must be equal to 0. That is my first equation, but HAA minus script E is common. So, you can divide throughout by that, and therefore, what does it give you? It gives you the result that CA minus CB is equal to 0, which implies that CA must be equal to CB, correct. So, as far as this value of script E is concerned, CA must be equal to CB, and now suppose I multiplied this row with that column and put it equal to 0, what is the answer that you are going to get? The answer that you are going to get is exactly the same. You will get the answer CA is equal to CB. So, even though it appears as if you have two separate equations, they are both the same, and therefore, the only answer that you will get is CA must be equal to CB. Now, if suppose you look for the other solution, how will you look for the other solution? The other solution would have, instead of a negative sign, you would have a positive sign. That means, instead of this negative sign, you are going to have a positive sign, instead of this also you are going to have a positive sign, and so if you multiply it, what will happen is that you will get the result CA plus CB equal to 0. Therefore, for the other solution will have what? It would have CA equal to minus CB, right. So, in one solution what has happened, CA is equal to CB, while in the other solution CA is equal to minus CB, that is all. Okay. So, what are those solutions? Let me just write them. In this case, phi is equal to, well, our expression for phi is, it is actually CA into 1s A plus CB into 1s B, but as far as this solution is concerned, we found that CA is equal to CB. So, therefore, this will become CA into 1s A plus 1s B. While for the other case, for this case, you will find that phi is actually given by CA into 1s A. See, in this case, CB is the negative of CA. So, therefore, the solution becomes CA into 1s A minus 1s B, that is the other solution. Fine. Now, what we can do is we can evaluate the expressions for CA. You can find the expressions for HAA and HAB. Just for the sake of completeness, I will write the expressions. I am not going to derive them, and these expressions are slightly more complicated. They are rather difficult to derive. It needs quite a bit of algebra. We will now look at the expressions for HAA and HAB. They are not very difficult to evaluate in this particular case. So, let us look at them. So, that will be the expression for HAA, and in this expression the R, of course, as you know, is the internuclear distance. R is the internuclear distance, and here is the expression for HAB. So, the expression contains S and delta, which are defined in the slide. So, this is the expression for S. S is actually the overlap integral, and delta is defined by this expression. Okay. So, I have written these expressions just to demonstrate to you that it is possible to evaluate HAA and HAB and express them as functions of internuclear distance. So, therefore, if I used these expressions in here, I would have Eg as a function of the internuclear distance, and once I get that, what can I do? I can plot this energy against R, against capital R, and that is what is done in my Mathematica file, which you will see in a second. And once you have obtained that, you can actually plot, right, you can plot the energy as a function of internuclear distance, and this blue curve which is seen in this Mathematica notebook is a plot of script E, right, script E with the subscript G, right, as a function of r actually in this figure it is plotted as a function of r which is given in angstroms. So, the horizontal axis is in angstroms, the vertical axis is actually in atomic units. That means, you will take that value and multiply it by, that is in atomic units. So, you will multiply it by 27.2 and that is your vertical axis. Horizontal axis is not in atomic units, it is in angstroms. And then you find that you get this blue curve. What is the blue curve? The blue curve actually shows that as you bring the two species together, the energy of the system, you can see it is decreasing, it reaches a minimum, and this point where the energy is the minimum must be the equilibrium internuclear distance of S2 plus molecular ion. So, therefore, theoretically by making this plot it is possible for me to find out the internuclear separation. Okay. And then you may ask me, what is this yellow looking curve, this curve? The answer is that that is a much more accurate calculation than what I have done here. This is approximate as I have told you, but it is possible to use a variational method and do a much better calculation. And if we did that much better calculation, this is actually the result. Okay. And you can do the same thing with the other state, the one that you called U, right. You can substitute the expressions and then plot EU also as a function of R, and if you did that you are going to get this magenta curve. So, therefore, what is the conclusion? Well, the conclusion is this is a very accurate calculation, much better than the calculation that we have done, but our calculation gives this curve. And if the system is actually having this as the state, if this is the state of the system, then there is the formation of a bond. But if you are thinking of the wave function for the electron to be not this function, but instead you say that the wave function is this, I have to distinguish between these two. So, therefore, this function I will call it phi g and this function I will call phi u. The reason for this notation I will explain. If the wave function is given by phi g, then there is a lowering of energy, while if the wave function is given by phi u, you find that there is no lowering of energy and therefore, no bond is formed if that is the way it is. Okay. So, now we have to look at phi g and phi u, but before I look at them in detail, I should know what this C A is, right, and what this C A must be. I have to find them. That will be my next problem, and how will I find them? The answer is that any wave function, it has to be normalized. So, therefore, what will I do? I will find C A in such a fashion that phi g is normalized, and I will find this C A in such a fashion that phi u is normalized. That should be the procedure. So, how will I carry out the process of normalization? Well, what I am saying is that take phi g, multiply it by its own complex conjugate and integrate over the entire space, but here it is not necessary to worry about complex conjugation because everything is real. So, therefore, you just take phi g, square it, integrate over the entire space, the answer must be 1. So, if this is your phi g, what will happen is that I would have C A square 1 as A plus 1 as B the whole square T2 integrated over the entire space, right. C A is just a constant. So, this must be equal to 1. So, if you took the square, what will happen? You will get C A square into integral 1 as A square d2 plus integral 1 as b square d2 plus 2 times 1 as b d2 integrated over the entire space. This must be equal to 1, correct. And as we have seen previously, 1 as a is an atomic orbit that is normalized. So, this integral must be 1, 1 as b also is normalized. So, this integral must be 1, while this integral is actually non-zero. It is the thing that we have denoted by the symbol capital S, and hence what do I find? I find that C A square into 1 plus 2 times S must be equal to 1, which implies that C A must be equal to 1 by square root of 2 into 1 plus S, right. I mean, if you add this 1 with 1, you will get 2, and so C A must be equal to that, and hence my phi g, let me remove this C A and say and put it there. So, this phi g must be equal to 1 by square root of 2 into 1 plus S. Now, in an exactly similar fashion, I can determine this C A. This C A will be determined in such a fashion that this orbital is normalized, and if you did that, it is fairly straightforward. You will find that this C A must be equal to 1 by square root of 2 into 1 minus S instead of a plus, and then of course, you will have 1 as A minus 1 as B, correct. So, this is my other function, and we will look at the nature of these two functions in the next lecture. Thank you for listening.